We have a classic odd function here to integrate, the inverse sine x or the arcsin x. I am Mr. Ish. Thank you for joining me. We're looking here at a limited domain -1 to 1 and a range minus pi over 2 to pi over 2. It's an odd function symmetric around the origin. When you're doing the integral, you're looking at obviously this area below and above the curves. There's an equal negative and an equal positive area. The end result of this integral should be 0. I will show you very quickly. If you are doing this by means of the single integral procedure, the most basic, you can do -1 to 1 arc sine x. That's the function you're doing the integral of, the definite integral procedure. The antiderivative for this would be determined by means of integrating by parts. It would really be x arc sine x plus square root 1 minus x squared. That's what it would be. And then you'd be looking at it from -1 to +1, and you can compute that. It will easily be a 0 and it will be right. You'll put 1 in places of x, then you'll put -1 in places of x, and you'll do the difference of those two groups and you'll have a 0. But if you want to do this by means of double integral, it's not hard. You'll break this into two different intervals, from -1 up to 0 and then from 0 to 1, and evaluate them separately. When you're looking here from -1 to 0, I'm doing a integral dx with respect to dy. My lower limit is a -1, my upper limit is a 0, but it would track the curve. Now, since I'm doing everything eventually with respect to dy, your equation should be x equals format. If y is equal to arc sine x, x is equal to, you push the arc sine on the other side, it becomes sine of y. That's your upper limit here, sine y. This is with respect to dx. Then you're going with respect to dy from a lower limit 0 to a upper limit minus pi over 2, 0 minus pi over 2. That includes everything from a -1 to 0 interval domain. Now let's look from 0 up to 1. In this particular instance, you have an upper limit 1 which is tracking straight up, so you don't have to do any modifications. The lower limit 0 is tracking along the curve, so that'll be a sine y. This is dx. And then you're going to go from 0 up to pi over 2 with regards to your dy integral. End result over here should obviously be a 0, and it will be here. The antiderivative is x. You're doing the upper lower limit, the difference. You'll have a sine y minus -1, which is a +1. This will become the integrand of your dy, 0 to minus pi over 2. I don't like the fact that I have a larger number here and a smaller number here. I could literally multiply all of this with a -1 and flip the limits around. I'll have a minus. Then here I'll have a minus pi over 2 and a 0. This part right here is good. Now let's look right here. The antiderivative is an x. You'll have upper lower limit difference, which is a 1 minus sine y. This is the integrand for your next integral with respect to dy. This is all you have to do. Come right over here. The antiderivative sine y is a minus cosine y. The antiderivative 1 is a plus y. There's a minus sitting outside. When we flip the limits around, we have a minus pi over 2 and a 0 plus right here. It's a y minus cosine y, which is a cosine y. We are looking at it from pi over 2 and a 0. All you have to do is just place the limits and compute. We're doing a minus cosine of a 0 minus cosine of a minus pi over 2. That's just a -1 coming from here. Plus, there's a minus sitting outside. 0 minus pi over 2 is a positive pi over 2. Come right over here. We have a pi over 2 minus 0, which is just a pi over 2, plus cosine of pi over 2 is a 0, minus cosine of is a 1. Open this up, you'll have a +1 minus pi over 2. 1 minus pi over 2 plus pi over 2 minus 1. Everything cancels out and your end result is a 0. Equal negative, equal positive area, end result will be 0. End results confirm the fact that we do have an odd function here. Minus a to a for an odd function, end result is always 0. You have a symmetry around the origin, you have symmetrical limits in terms of character, appearance, function and behavior, all of that. Thank you.